Hello everyone, welcome back to Zeta Factor, and today I will be talking about my favorite theorem from number theory, and this is a Fermat Little Theorem. Who is Fermat who created the theorem in the first place? So Pierre Fermat is a French mathematician who lived in 17th century, and he made significant impact in the development of modern number theory and modern mathematics as a whole. Let's look at his theorem. So Fermat Little Theorem is saying that if p is a prime number and a is any integer not divisible by p, then a in power p minus 1 is equals to 1 modulo p. So we'll go through the proof today of this statement. So first is that we may assume that a is more than 0 and less than p minus 1. This is simple consequence of the modular arithmetic law. So basically we may just reduce a modulo p if that's not the case, and then after reduction a will become in the range of from 0 to p minus 1, and this is the same as reducing a in power of p modulo p, which is a trivial statement. So basically we may just assume this statement in the first place. To prove the theorem, we will use a method of mathematical induction, and then we will prove the theorem for all integers a more than 0. The base step is basically a equals 0, 0 power of p equals 0, modulo p. It's trivial. So next we must show that if the problem is true for a equals k, it is also true for a equals a k plus 1, and this is like induction step, and then if we prove that, we will prove the Fermat Little Theorem. As a part of this proof, we will use also this lemma, which we will prove later, which basically for any integers x and y, and for any prime p, x plus y the power of p equals x power of p plus y power of p modulo p. You might notice that if you simplify this expression, this will not be equal to this x power of p plus y power of p. In normal arithmetic, this will be actually a binomial theorem. But if we look into the equality modulo p, this is actually equality holds. So the proof of Fermat Little Theorem is the following. So let's assume that k power of p equals k modulo p, and consider k plus 1 power of p. By the lemma, we know that it equals k power of p plus 1 power of p modulo p, and this is clearly 1, it's obvious. Then k plus 1 p equals k plus 1 modulo p, because this is equals k by the assumption. And then basically this is proves the Fermat Little Theorem for k plus 1. So theorem is proven. Now we need to prove the lemma, that x plus y in power of p equals x power of p plus y power of p modulo p if p is prime. We need to apply binomial theorem. So x plus y in power of p equals sum from 0 to p. Then let's consider this binomial coefficients. From p to I equals p factorial, I factorial, p minus I factorial. So we see that always there is a p in numerator. And then in denominator, all these numbers I less than p, which means pi will always be divisible by p, which means that x plus y power of p, it's always divisible by p in those cases. So x plus y power of p would be x power of p, plus there would be the binomial coefficients plus y power of p, but all of them are divisible by p. So basically will be equals to 0 modulo p. That will conclude the proof. Because every single coefficient except those two, which are equal to 1, so all the coefficients where we have these conditions are between 0 and less than p, and p minus 1 less than p and 0, we will have this condition work. So, but we proved this lemma, and then we proved a Fermat Little Theorem. Thank you for listening. You've been on the Zeta Factor channel.